Hi everyone, I'm Stan Kitchen, retired research botanist for the Forest Service Rocky Mountain Research Station. And I'm happy to be here today, and I'll be talking about wildfire. According to David Bowman, fossil charcoal indicates that fires began on the Earth soon after the appearance of terrestrial plants, and combustion becomes possible when atmospheric oxygen concentrations are above 13%, and variations in oxygen levels correlate with fire activity throughout the history of the Earth. Millions of years later, atmospheric oxygen was thought to exceed 30%, making even moist vegetation flammable, and high percentages of charcoal in Permian coals reveal abundant fire activity. In short, fire has impacted the Earth's biosphere for a very long time. So how do we, you and I, see fire today? Thanks in part to the media, fire is typically viewed through a single cataclysmic lens. This view is oversimplified and just plain wrong, and it leads to the misunderstanding that fire is somehow unnatural and always unwanted. A more correct view can be found in the words of Bob Keane, quote, "The ecological role of fire is to function as an extrinsic disturbance factor. It is a keystone disturbance that recycles nutrients, regulates succession by selecting and regenerating plants, maintains diversity, reduces biomass, controls insect and disease populations, triggers and regulates interactions between vegetation and animals, and most importantly, maintains biological and biogeochemical processes. Fire is neither good nor bad. Fire is an important ecological process that can produce variable effects. The value of these effects must be interpreted in the context of human desires and needs." End quote. My purpose today is to talk about a certain kind of fire, surface fire, as it is, or once was experienced in forested systems across southern Utah and, for that matter, much of North America and elsewhere in the world. First, I'll characterize what constitutes a surface fire. Then, because surface fires are much less common in today's forests than in the past, I will touch on one method commonly used for assessing historical patterns of surface fire and look at some southern Utah examples of long-term surface fire histories. So what is surface fire? Surface fire in a forest is fire which burns through the living and dead fuels on or near ground level, leaving unburnt and usually alive the mature tree canopy above. Surface fires are typically classified as low intensity, meaning low heat output and short flame lengths, and low severity, meaning immediate impacts on living organisms and soils are relatively muted. Surface fires are most common when fuels and weather conditions are such that flames are not carried to the canopy. Here we see a site 22 years after surface fire with surviving mature trees, logs of smaller trees that were killed by the fire and have since fallen, and recovered understory shrubs and herbs. In contrast, high fuel loads and ladder fuels produced a high-intensity crown fire on this site. All mature trees were killed as the fire spread actively through the canopy. Succession and ecological function will be very different here than at the last site, even though the pre-fire species composition was very similar. With eons of exposure, tree species evolved adaptations to different kinds of fire. For example, lodgepole pine is adapted to high-severity crown fire via specialized serotinous cones that only open and release seeds when exposed to extreme heat, promoting rapid synchronous regeneration. In contrast, ponderosa pine has multiple adaptations for low-severity surface fire, including thick insulating bark, self-pruning of low branches, an open branching pattern, and a deep root system. Mature ponderosa trees typically survive surface fire, and new recruitment may be sporadic and timed to long fire-free periods. Although adapted mature trees are not usually killed by surface fire, they often experience localized injury, such as needle scorch on low-hanging branches. Another kind of localized injury is heat-induced death in a portion of the growth layer or cambium sandwiched between the woody center of the trunk and bark on the outside. Among other things, the cambium is responsible for production of new layers of wood, which we see as annual growth rings. When the cambium dies, wood production stops, and within a few years, the bark is sloughed off, exposing the wood beneath, as seen here. These wounds or fire scars are typically found at the base of a tree on one side. Once a tree has been injured in this way, it becomes susceptible to additional injury by subsequent fires. In this way, a single tree may retain a clearly discernible chronosequence of fire-induced injuries in its growth rings. Fire ecologists refer to this grouping of injuries on a tree as a cat face. I'm not sure why. Trees with cat faces are commonly scattered among similar-sized trees with no obvious injuries and are valuable as fire-recorder trees. Standard techniques are used to extract cross-sections that cut through one or both sides of a cat face, and to assign years to the growth rings associated with each fire-induced injury. Thus, long-lived trees, or recorded trees, are especially useful because they provide annually precise records of surface fire that cover multiple centuries, and that correspond to variability in climate and human land use patterns that drive fire regime variability. There are, however, limitations to this method. First, the record from any one tree is incomplete, as it may not record all fires that burn near it. And second, that record is spatially limited, restricting interpretation of spatial variability in fire patterns. Both limitations are largely overcome by sampling multiple recorder trees, including living trees, snags, stumps, and logs, from across the broader landscape. An added benefit of sampling multiple trees is that the composite fire chronology often covers a longer period than any single tree alone. In this slide, we see both a topographically variable landscape and a fire history chart showing all fire records extracted from it. The long horizontal lines represent the lives of individual trees, or in some cases small clusters of trees. Vertical hashed lines are years of recorded fire. Intensive sampling such as this facilitates detailed examination of fire variability through time and space across complex topographies. Now let's look at a few examples in our area of interest, South Central Utah. With the help of Dennis Bramble, I took cross-sections from this log and a nearby stump located a little over a mile northeast of the top of Canaan Peak, in a mixed conifer forest opening at about 8,400 feet in elevation. The log dated to the year 1505, with the first fire recorded in 1613. Between the two records, I identified 27 years with fire, 12 of which were recorded on both trees, and the last being in 1871. During the 258 years between the first and last fire year, average fire interval was almost exactly 10 years, with shortest and longest intervals of 4 and 21 years. This picture was taken in 1996 by Charles Kay, near one of the many small lakes near the southern rim of the Boulder mountain top. Elevation is 9,600 feet. And this picture was taken 124 years earlier at the same location by John Hillers. You can see the change in forest composition and density. In 2006, I sampled 9 old fire-scarred trees from all around the lake, 8 Douglas fir and 1 aspen. The earliest fire recorded was 1708. Years in which fire was recorded on multiple trees, suggesting widespread burning, occurred in 1768, 1812, 1841, and 1869, the last being just 3 years before Hillers took his photo. Using just these 4 fire years, an average fire-free interval of 34 years can be estimated over this 100-year period. Next, I move west to a site at School Wash, located in Ponderosa Pine at 7,300 feet on the east flank of the Markagon Plateau. Here we sampled 9 trees with 30 recorded fires between 1528 and 1879. Average fire interval was 12 years. and as we observed on previous sites, the pattern of frequent surface fire ends in the late 1800s. Now I go north to the Tusher Range. This is an aspen mixed conifer site on a south-facing slope between 8,900 and 9,300 feet. For this site, I cross-dated 15 fire-scarred trees and found 22 fire years recorded. Fire years started in 1626 and ended in 1878. Surprisingly, the average fire-free interval for this higher elevation, more mesic site was still just 12 years, and again fire stopped in the late 1800s. One final example that I will use today began in this small stand of old ponderosa pine trees surrounded by aspen. In 2017, Chad Reed asked if I would take a look at a few trees he thought had fire scars. I ended up extracting samples from one live tree and a nearby snag. The results were consistent with what I was seeing elsewhere with aspen, but perhaps a bit surprising for some. Conventional wisdom holds that fire rarely burns in aspen without heavy conifers. On this nearly flat site, I documented 19 fire years with an average fire-free interval of 11 years. And as before, the last fire was in the late 1800s. Chad was eager to fund an expanded study across a large chunk of mostly private lands east of Cedar City, commonly referred to as Cedar Mountain. For reference, the study area is north of Zion National Park, east of Kolob Reservoir, and mostly south of Navajo Lake, covering about 100 square miles. During 2 summers, I secured samples from 122 trees, spanning 3,000 feet in elevation, including combinations of aspen, mixed conifer, gamble oak, and ponderosa pine forests. I successfully cross-dated samples from 115 trees. Fire years from those individual trees were combined into 38 composite fire chronologies made from 1 to 10 trees each, based upon their close physical proximity to each other. On the right, we see the composite records arranged from top to bottom by declining elevation. Surface fire was common in all forest types. As seen in the figure to the left, fire-free intervals tended to be longer on average at higher elevations, but even then, the evidence strongly supports an interpretation of a landscape shaped by fire. These 2 cross-sections are typical, with the one on the left taken near the upper elevation limit and the one on the right from about 7,000 feet. Note the high frequency of fire for both cross-sections. Surface fire was recorded somewhere in our Cedar Mountain sample area for 198 different years. The oldest recorded fire was in 1447, and the most recent in 2002. Fires occurred in 142 of the 251 years between 1650 and 1900. Small fire years were most common, but there are numerous examples of years with larger fires, and some occurred across the study area and likely beyond. Examples include 1715, 1735, 1777, and 1813. Although assessing burn area is near impossible for past surface fires, I used an annual fire impact index based upon the number and physical dispersion of fire-scarred trees for each fire year. These indices serve as imperfect yet useful surrogates for actual area burned. Here we see the total number of fires per decade on top and summed 10-year fire impact score on bottom. This way we can see that although fires continued at a reduced rate into the 20th century and on these privately managed lands, fire impact or area burn drops off sharply before 1900, and current vegetation reflects that reality. I end with just 2 questions. First, who or what started all these fires? Time does not permit me to go into the details, but evidence increasingly supports the idea that the historical fire regime was a product of both lightning-caused and abundant human-set fires. And secondly, what purpose or purposes were satisfied using frequent surface fire as a tool to modify or manage landscapes in the past? And what might we learn from this as we attempt to manage for resilience under an environment of increasing stress today and into the future. Thank you for your time.